somehow lower.
When you talk about what?
State music. State.
Oh, mixing.
Yeah, state music. We talk about another for the valence nucleons, and what about those that are in closed shell?
Okay.
What you those when you assume some collective motion, you assume not only the valence but all the nucleons are
Okay, so
participating in the
okay, so good question. It depends on two things. One is the kind of collective motion and on how good a model you want to have. A simple approximation is only taking into account the valence nucleons. Of course, particles from the closed shells can be excited up into the valence shell, or even above that, or above that. And those will generally be small amplitudes in the wave functions. The mixing will be small, but not zero. So if you want to have a better calculation, you should include those. Generally, two things happen. If you want to include more states, the matrix you have to diagonalize gets bigger and bigger and bigger. And already it's too big even in the valence shell. If you're in the middle of the valence shell with a nucleus like 166 dysprosium, which has 16 valence protons and 18 valence neutrons, already we can't do it. It's too many. So you have to make some approximations. The other thing is, generally these calculations involve some parameters. And if you go from the valence shell and start including other shells, usually you'll have other parameters. And so then you have a question of how many parameters do you want to have for a given quality of agreement. And I'll show you something later about elephants. They're related to the number of parameters. Okay?
Maybe. So when you go, when you take something proton, and you take, for example, the ground band, and you go up on it, so you have this, let's say, monotonically changing of the momentum, sorry, not the momentum, but the inertia, because of this centrifugal stretching. But at some point, you have a sudden change. You can definitely see that. So the energy growing. Oh,
Are you talking about backbending?
What?
Are you talking about backbending?
I'm not sure what I'm talking about. At least I imagine this, maybe it's something like a pair breaking, but the pair breaking energy is much more small than this pair breaking appears.
Okay, so I guess you're talking about backbending, but maybe you don't know the words. So imagine a deformed nucleus with a ground state band. The angular momentum goes 0, 2, 4, 6, 8, and so on. The energies, excuse me. Oh, geez, sorry about that. I guess you're all awake. The energies go as J times J plus 1, which is like J squared. So those energies get very big. Imagine a nucleus in, let's say, the 10 plus state, which involves two particles in H11 halves. Okay? You could take a particle in H11 halves and another one in H11 halves and couple their angular momentum to 10 plus. It may happen that it takes less energy to break that pair and make a 10 plus state than it does to have 10 units of angular momentum. Okay? And then you'll get a sudden change in structure. Okay? And the energies will increase like a rotational band with some centrifugal stretching up to the 8 plus state. The 10 plus state, so the 8 plus state will look like the ground state with 8 units of angular momentum, rotational angular momentum. The 10 plus state can look like the ground state with a broken H11 halves pair and 0 units of rotational angular momentum. And then the 12 plus state would look like that 10 plus state with 2 units of angular momentum, rotational angular momentum. So the spacing between the 10 and the 12 can be like the spacing between the 0 and 2. So you can get these changes in structure as you go up in energy. Is that your question?
Yes.
It's called backbending.
Backbending.
And the reason is this. If I plot the gamma ray energy between successive states, it goes up, right? So if I plot gamma ray energy along this axis, and the spin of the states along this axis, yeah, right, okay? That will be a line which will go up. But then if you get that change in structure, those levels become closer together, it comes back, and then it starts up again. And this looks like a back bend. Okay? Other questions?
Yeah, I was just wondering, do nucleon-Cooper pairs exist? Can two nucleons combine to make a boson?
Okay, so the answer first of all is yes. Second answer is you've already seen this.
Yeah.
When we talked about two nucleon systems, the lowest state was 0 plus. That was a particle in some angular momentum, and the other one coupled like this. That's a Cooper pair. It's exactly what it is. There is a model which we will, I hope, talk about today called the interacting boson approximation model, IBA. Who's heard of the IBA model? Who's ever done a calculation with the IBA model? Oh, that produced it. Virgil, you didn't raise your hand. Okay. So we'll talk about a model called the IBA, which makes the approximation that you can treat all of the nucleons, all the valence nucleons, as in pairs as bosons. But not coupled only to angular momentum 0, also coupled to other angular momentum.
But like, if there are bosons, then it could exist in the same place. At the
Yes.
same time. Okay, that works out somehow.
Yeah, yeah.
Yeah, if I can
Yeah,
also
sure.
have one question. This one might be a bit out of scope, I don't know, but like I asked Tim today about if like neutron only cores could exist, nuclei could exist, and I was just wondering, might neutron stars be an example of that? Are neutron stars like totally non-charged, or?
No. The word neutron star is really not a very accurate name. Neutron star is a very complicated animal. It's got many different layers, and some of the layers have one structure and some have others. There are many protons around. There are certain parts of the neutron star that look like very, very rich neutron matter. Okay.
Thanks.
Other questions? Yes?
Yeah, I have a question about multi-particle states. So it was possible that we have like states with all more states with the same given angular momentum, but I'm not able to visualize these states. Are these states at the same energy levels and then mixing together, or?
No. There's no blackboard, is there? Okay, so I'll do it with my hands. So let's imagine four particles in, say, a G9 halves orbital, okay? And let's talk about making a state with angular momentum 4 plus. Let's say 6 plus, okay? So I can take two particles and couple them to, well no, let's do 4 plus. I can take two particles and couple them to angular momentum 0. Okay? Take the other two and couple them to angular momentum 4. Those two together will make an angular momentum 4 state. What will be the energy of that state relative to the ground state? The ground state has all of them coupled to 0. Okay? And if you remember what the level scheme looks like for two particles, it's 0, 2, 4, 6, 8. So the energy of that 4-particle state would be this plus one of these distances from here to the 4 plus. Okay? We can also make a 4 plus by coupling 2 particles to 2 plus, the other 2 to 6 plus, and add the angular momentum this way. The energy in that state will be the sum of the energy to the 2 plus for the 2 particle system, plus the energy to the 6 plus. So that will be a much higher state. Okay? And you can go on and on and on. So the answer is they will not be at the same energy. The toy model that I talked about, where I had n-degenerate states, and one came way down, that was just a toy model to make a point that the mixing produces a lower state. In real cases, those levels will not be degenerate. And one proof of that is the answer to your question about BE2 values. BE2 values between rotational states are a couple of hundred times larger than for a single nucleon change of orbit. If all the states of a given, say 2 plus, were all really degenerate in samarium 154, which has 3 times 10 to the 14th, then that BE2 value would be 3 times 10 to the 14th larger. But it's only 200 times larger. So you can see that this toy model is really, really, really approximate. But it has the physics right. Okie dokie? I have a question for you. Who worked out the allowed spins for 3 quadrupole bosons? Be honest. I know you know the answer because it's in the slides. Who actually sat down and worked it out? Oh. Well, I have to tell you, I didn't work on my slides at all, so I am going to talk to you. Okay. Bad. Okay, next question. Work it out, it's fun. I don't know if it's fun. You may not think it's fun, but you'll learn something. Her hand was up first and yours.
So this would be maybe a question for yesterday's lecture, but as you said that they shouldn't be nuclei with more than 104 protons.
Yes.
So do you have a kind of explanation for this?
Magic.
Okay.
No. There's a real explanation. So, if all of the levels in the independent particle model were uniformly spaced, and they all could hold the same number of particles, okay? Nuclei with Z greater than 104 would not exist, because the Coulomb force would explode the nuclei. However, if you remember from the independent particle model, the levels were clustered in groups. And if you have a cluster of levels, and you put particles in it, the energies there will be lower than if those levels were like this. So you gain energy due to the quantum mechanical properties of principal quantum number and orbital angular momentum. Okay? Yeah.
Sorry, it's just connecting to this. So, as you said that you will explain why the neutron-rich nuclei are interesting, this pretty much the same for the high proton for the high proton containing nuclei, and there are more and more. Is it meaning a new theory, or it's still connected to the clustering and just kind of pushing the limit how much protons can be in there?
I'm not asking what about the heaviest nucleon?
Yes. About how many, because as you said that if they make a nuclei with a lot of protons, it's on the headlines, so it's very important.
Okay, so I'm not going to talk about that. You can calculate by doing not toy calculations, but real calculations, the stability of those heavier nuclei. And all the theorists, once a nucleus has been found and found to be stable, the theorists have a remarkable ability to predict that it's stable. They're very good at that. Okay? When you go beyond that, the theories just differ completely. And next time I'll show you an example of how the theories differ once you start extrapolating. Okay? I'll also show you a way to change extrapolation into interpolation, which is much more reliable.
Quite nice question. You refer to the nuclei as, or particles inside as having trajectories of circular or ellipsoid shape. I know we haven't truly noticed the shape of we know it's a sphere of the nucleon, but that's all we know pretty much about the geometry. But I cannot stop thinking about the electron configuration in the atom.
The which configuration?
The electron geometry or the geometries, and they are far away from spheres, except for the first one. And I'm thinking, why wouldn't the nucleon behave like that, having strange, should I say, shapes of the trajectories of the particles inside? Why are we choosing to model them as, or if they are in reality like that, as spheres and circles, and not something much more complicated as seen from the electrons?
Interesting question.
If I may, if you consider all the interactions, it's kind of unlikely to have spheres or slightly elongated spheres or circles.
Well, let's make a distinction between circular orbits, which mean orbits in a given plane, and a spherical nucleus. Those are not the same thing.
Yeah.
So let's take a doubly magic nucleus, which is a sphere. And let's add one particle. That particle goes in some plane. Okay? And so that nucleus immediately will be oblate, disc-shaped. Has to be. That orbit, as far as I know, is circular. Yeah, I think it is. I don't see any reason why it wouldn't be. If you look at it from the point of view of the frame of reference of the nucleus, that's a circular orbit, and so the nucleus will look like this, like Saturn, okay? So it'll be disc-shaped. However, in a laboratory system, that orbit can be oriented any different way, and so the net result will be spherical.
Yeah, but the same thing we can say about the atoms and about the electrons. We see the electron cloud as a sphere in an atom, but if we could walk inside an atom, we will not see the electrons doing circular paths. We will see very strange shapes, like number 8 or something like that.
Oh, wait a minute. There's a difference between what you talk about as the orbit of the electron and the shape of the electron wave function cloud. And I'm talking about the time average cloud.
Oh, you're not.
Because these wave functions have nodes, and so they have complicated shapes inside.
Yeah, like distribution area in specific areas. I'm expecting to see the same thing with the nuclei.
Yeah, I think that you do, but I don't think it's non-circular. That's in the radial direction they have nodes. I need to think about this. I want to think about it before I say any more. Okay. Other questions? I think let's start the lecture at 2:20, so there's time for one or two more questions. Sorry? Well, I just want to make sure everybody has a chance. Any more questions? Last chance? Going once, twice. But the measured quadruple moment will look like an omelet. You have to use a certain formula to correct it. So there is a very important difference between the laboratory frame and the nuclear frame. In fact, the very first thing we're going to do is related to that difference. So you'll see an example, a different example, but an example. Okay, I think we should start because there's a lot. You've asked me to add some topics, and so there's a lot to cover. Now I have to do something very complicated today. I have a pointer, which has a nice bright thing. I have to use this hand to change slides. So I hope I don't get too confused. It's easier than doing this. Okay, so these are the topics we're going to cover in the rest of the lectures today and tomorrow. And start with this, then we'll go to this, then we'll go to this, and then we'll go to this. Not surprising. Okay, so I want to come back to this. This was a question Maria asked me at the end yesterday. She said, well, this looks very nice. You have a ground band, you have this gamma vibrational thing, and then rotational states. You have this beta, which is an oscillation like this, and then the states. But how do you, as an experimentalist doing an experiment, figure that out? What you really will see will be 0, and then a 2 plus, and then a 4 plus, and then a 6 plus, and the next energy level here will be a 2 plus, and then a 3 plus, and then an 8 plus, and then a 4 plus, and then a 5 plus, and then a 0 plus, and then a 2 plus, and then a 6 plus, and a 4 plus. And that may not be very obvious how you split that into 0, 2, 4, 6, 8, 2, 3, 4, 5, 6, 0, 2, 4. So I want to give you some ideas about how you can do that, okay? So this is the kind of thing we want to end up with, and I'll give you some ideas how you can do that. For example, another question is, how do I know that this 4 plus belongs to this band and not that 4 plus? Well, in this case it's pretty obvious, but suppose this 0 plus level were here, then this 4 plus and this might be almost at the same energy. How do I tell? So I'm going to give you some guidelines. Okay. These are general comments and also some very, very specific comments about collective states. So collective states arise from mixing. And mixing lowers the energy of the lowest collective states. Okay. So that implies a couple of things. Since they come from mixing, they should be low lying. So we're looking for states low in the spectrum that, for example, don't fit into a pattern of 0, 2, 4, 6, 8, and so on. Okay? We're not looking at states up on the 4th floor. Okay? We're looking for low-lying states. Okay? The lower in energy, the more collective. Think of that model with n states mixing, and the larger n is, the more collective the state is, the more terms in the wave function, and the lower its energy. So as a general rule, it's a little bit more subtle, but as a general rule, the lower in energy, the more collective. Now, collectivity inherently involves wave functions with many components. That's the statement of the same thing as mixing. But now, if you think about that, those are components corresponding to particles in many different orbits. Many states mix. Now, think about that. We have a ground state. We have some vibrational state up here, whose wave function consists of a mixture of many, many different components, configurations. Okay? And these will involve particles in this orbit, this orbit, this orbit, and so on. Now I go to the next nucleus, the next state, even nucleus. I go from samarium with Z equals 62 to gadolinium with Z equals 64. Okay, so over here in the shell model, I've added 2 protons. Okay? That's not a very big change. This thing involves many, many components. Its wave function won't change very much. Maybe some orbit will be blocked because the protons are now filling it, but in general it won't change much. Is that clear? In other words, let's take this room, and I take a photograph of the room, and now I add 2 more people. Basically, the photograph looks pretty much the same. Okay? So, a feature of collective states is they don't change much from one nucleus to a neighboring. Now, there can be cases where they do, and if they do, that tells you something. But in general, they don't. So you can use guidelines from the neighboring nucleus to help you. Here's an example of this. So, let me come back to here. Ground band. This excitation is the so-called gamma vibration, which is one where the axial asymmetry is lost. Okay? And the other one is a beta vibration where the elongation changes. Okay? So I'm going to look at data on a large number of nuclei and ask, how does the energy of this state change? How does the energy of this state change? Okay. This is the energy of the gamma vibration from mass 150. Who's on? Oh, Steve Irons. Ah, hi, Steve. Bye, Steve. Okay, so this is the energy of the gamma vibration from mass 150 up to 190 or so. And you see how smoothly it varies? Okay? Pretty smoothly. This dashed line is my way of telling myself that something different is happening here than here. We don't need to worry about that. Just notice that it's very smooth. Also notice that the average energy in the middle of the shell is about 800 kilovolts. Okay? That's the gamma one, the one that starts with 2. This is the beta, the one that started with 0. And again, it's pretty smooth. It's a little more chaotic than the gamma band. And also the energy is a little higher. It's around 1100 kilovolts. This is around 800 kilovolts. So already we can anticipate something. This has come down lower, so it's probably more collective, has more components in the wave function. This is higher, is less collective. Okay, now think about this room again. Suppose instead of having 30 people in the room and adding 2, which wouldn't change things much, suppose you 2 were the only ones in the room and 2 more people came in, there'd be a big change. Okay, so when you have a state which has fewer components and you add 2 more, change a couple, it will change by more. So the less collective a state is, and generally the higher it is, the more it will also vary in a kind of chaotic way. The gamma band is much more collective and behaves very smoothly. Is this clear? Okay. Notice the beta bands are 1.5 times as much, higher, and it fluctuates more. This points to the lower collectivity of the beta vibration. Okay, now this is very explicitly a topic Maria asked for. I want to talk more about the energies of collective states, gamma ray transitions between them, intraband, interband. Does everybody know the difference between intra and inter? You know which is which? Intra is within. Like you play intramural sports. Is that a word you know? That's within a college. Intercollegiate sports are between schools. Okay? So intra is within, inter is between, you'll see what I mean. Something called the Euler rules. Okay, so here's the nucleus with some levels, and since I did this quickly last night, I just didn't want to bother to put superscripts on all these, but they're all positive. Okay, so first of all, imagine, I should have had all these lined up together and then separated them. So imagine that you have 0, 2, 4, 6, 2, 3, 0, 2, 4, and you try to make some sense of it. So what can you do to try to sort this out? Well, you can see from here that the 4 to 2 ratio, R4-2, is about 3.33. So we know it's a rotational nucleus. Okay, so we know that the energies of rotational states go as, look how lazy I was, h bar. H bar squared over 2 times the moment of inertia, J times J plus 1. Okay, now we can do a calculation, which you did partly yesterday. If I calculate the energy difference between 2 and 0, that's this energy difference, it's 6 in units of this, right? 2 times 3 is 6, 0 times 1 is 0, 6 minus 0 is 6. Interestingly, 3 minus 2, this spacing is also 6. Right? 3 times 4 is 12, 2 times 3 is 6, 12 minus 6 is 6. 4 minus 3 is 8. That's 4 times 5 is 20, minus 3 times 4 is 12 is 8. 4 to 2, which I meant to put here but forgot, is 20 minus 6, so that's 14. So the first thing you can do is by looking at the energy spacings, figure out which ones are rotational states of each other. So for example, if I have this 2 plus state, and this 3 plus state, and this 0 plus state, and this 2 plus state, and I want to ask, which band does this 4 plus state belong to? I know it's a deformed nucleus, and so I can use this spacing to get h bar squared over 2i and predict where the 4 plus state would be, or I can use this spacing. But clearly, if I use this spacing, the 4 plus is going to be up there somewhere. And so just from the energies, it's pretty clear that this 4 plus 8 belongs to this group. Is that clear? Yeah? Anybody not clear? Okay. All right, so the energies, oh, sorry, let's just use this. The energies already give you a clue as to how you can organize the things into bands. Okay? All right. Transition rates. These transitions, which go within a rotational band, are the intra ones. The rotational motion involves the entire nucleus. And so that's going to involve a lot of collective components, and those transition rates are very, very large. If you know about BE2 values, I mentioned it in the first lecture, the BE2 values are very large. These are the ones that are a couple of hundred times what would happen if a single particle changed orbits. Okay? So if you measure the lifetimes of these states, or use a technique such as Coulomb excitation and directly measure the BE2 values, the ones that are about 200 units, we use a unit called Weisskopf units, those are the ones which are rotational, those are within a band. So that would allow you to put these transitions in this band. What about the others? Okay, the ones from the gamma band, and I just illustrated these, are on the order of 15. Okay? Because these excited vibrational states are made up mostly by exciting the valence nucleons. And there are not so many of them, so they're not as collective. You can tell they're not as collective because they're higher in energy, and their collectivity as measured by these BE2 values is smaller. What about the beta band? Well, remember it's a little higher, less collective. Typical values are about 2. Okay, so if you measure the BE2 values, that gives you another way of sorting it out. Okay? Everybody with me? Wave functions. And now we come to a question which somebody asked down in the front. One of you two. About the intrinsic and the laboratory system. So think of this nucleus. It can rotate and it can vibrate. Now, in general, if you imagine it rotating and vibrating at the same time, and it gets longer as it rotates, and then it gets shorter, it gets longer, those two motions are going to be very coupled, very confused. But it doesn't happen like that. The rotational motion is about 4 orders of magnitude different in frequency than the vibrational motion. So it's a very good approximation to separate those two motions. Okay? And so what we almost always do in discussing the wave functions of nuclei like this is we write the wave function as a product of 2 parts. One describing what's usually called the intrinsic character. That means equilibrium ground state, gamma vibration, beta vibration, and one describing the rotational part. 1 second. Okay. So I write the wave function as chi, it's the usual notation, for the intrinsic, and d, these are the linear d matrices, but you don't need to know that. Something describing the rotational part. Yes?
Sorry for the interruption.
No, don't be sorry. Tin's task.
You said you analyzed 2 motions as completely separate motions, the vibration and the...
I didn't say completely separate. I said largely.
Yeah, largely separate. But what if the one of the motion is got a phase that is, or a frequency that is a multiple of the other, so at the end, you have a specific shape of the...
You want to talk about something like beats.
What?
Beats. Maybe you don't really... If you have 2 frequencies which are multiples of each other.
Yeah, so at the end you have some kind of oscillation of that's synchronized on some part. So for example, for the simplest example of the rotation and the elongation of the ellipse, it will have not a circle, but a wave line of the shape of the nucleon.
Yeah, I guess that can happen. I've never thought about it. I've never seen it. I'm not sure what the observable signature would be. I guess it could exist.
So we don't know.
I don't know.
Okay.
Interesting thought. Okay. So I want to look at these wave functions, and from these wave functions, we can derive something that's very interesting that helps us decide also which of these levels belong to which band. Now I want to ask you, who knows about Clebsch-Gordon coefficients? Raise your hand high so I can see. I. Is your hand up? Okay. Aye, Clebsch-Gordon coefficients. I want to see. Raise them up again. I want to see. Okay, so about half of you. Okay. For those who don't know about them, I will say some words like this, and you'll just have to learn to live with it. Okay. Okay, this looks awful, and it's not complicated. Okay. So I want to describe the wave function as a rotational part and an intrinsic part. Since the nucleus can rotate either direction, and the particle can go around this way or this way, there's always a symmetric part with the opposite direction of motion, and we will not worry about that at all, so just forget that. We want to talk about E2 transitions, and so we have a matrix element from an initial state with an E2 operator to a final state. Okay? All these silly little quantum numbers, I, M, K, are really not so important, so I'm just going to use K. So this matrix element is now going to be an E2 operator with the initial wave function on one side and the final wave function on the other. Okay, initial wave function is this little subscript I, final is F. And now I've got two terms here, these two terms, I've got two terms here, these two terms. So I'm going to have four terms altogether. Okay? It turns out, and I can tell you why if you want, but I don't really want to have to do it. The cross terms, this with the second one will give you 0. The second one with the first one will give you 0. And so we only have the two direct terms. This one with this, and this with this. And those two, this with this and this with this, give you the same number anyway. So it all comes down to one term, which is that the matrix element is equal to, and I just use the first term, the wave function of the final state and E2 operator of the wave function of the initial state. Now comes the beautiful thing. The beautiful thing is these rotational and vibrational frequencies are different. So we can define the orientation of the nucleus in space separately from the amount of oscillation of its shape. And so we have this product form of the wave functions, and so we can write this as a product of two matrix elements. An intrinsic one, this has to do with the matrix element for going from, say, a gamma vibration to a ground band, ground state, and this has to do with changing angular momentum. These things are what are called Clebsch-Gordon coefficients. And if you don't know what they are, what you can think of is when you have two angular momenta coupled to a third angular momentum, there is a certain quantity coming from the theory of angular, quantum mechanical theory of angular momentum that tells you how likely that is. The main point to think about for that is it has nothing whatsoever to do with nuclear physics. It's just quantum mechanics of angular momentum. So this part is a number. You can look it up in a table. And I'll show you the table later. This part has to do with the nuclear structure. This in general is very complicated to calculate. What we're going to see is we don't have to calculate this. Okay, so let's calculate the relative BE2 values from this 2 plus of the gamma vibration to the ground state 0 plus 2 plus and 4 plus. Right? We're doing E2 transitions, so you can change the angular momentum by 2, by 0, or by 2 the other way. Okay? That's what we're going to calculate. A comment on the side. If you're an experimentalist and you're measuring gamma ray intensities, remember that these relative BE2 values are not the relative gamma ray intensities. The gamma ray intensities go as some constant, oh, that's supposed to be equal, go as some constant times E gamma to the 5th times the matrix element squared. So you always have to get rid of this E gamma to the 5th term. Okay? So, for example, this transition, which has... I'm sorry?
If you don't have anything.
We're talking E2 transitions.
But in
Yeah, but the low line levels of deformed nuclei are almost always pure E2 or 99% E2. If you have mixing, you have to take the E2 part. Okay. So you always have to worry about that. And that has the effect that these transitions, which are very low energy, are often very hard to detect. But as you'll see in a minute, they're very important. Okay? This energy might be 1 MeV, this might be 100 kilovolts. So that's a factor of 10, that's 10 to the 5th, just due to this stupid e to the 5th factor. Okay, because you have to get rid of it. Okay, anyway, let's calculate the ratio of 2 of these BE2 values. So I'm doing initial state, 2 plus gamma, to a final state, 1 of these, divided by the relative BE2 to the square root of it, from the same initial state to a different one. I have a prime on the F there. So that would be like this to this. This matrix element is the product of the rotational part and the intrinsic part. This is the product of the rotational part and the intrinsic part. But now look what happens. The intrinsic wave function for the initial state is the gamma vibrational wave function. The intrinsic wave function for the final state is the ground band. So these two matrix elements are the same. Because these transitions go from one state to 2 states in the same rotational band, same intrinsic state, this cancels out. So lo and behold, this branching ratio, by branching ratio I mean the BE2 ratio, is just the ratio, the square of this ratio. And these are Klebsch-Gordon coefficients. So the ratio of those BE2 values is just, this is the notation for Klebsch-Gordon coefficients, just the square of that ratio. And in this case, excuse me, 2 gamma to 0 ground over 2 gamma to 2 ground is 0.7. And that's why you see 2 gamma to 0 ground, 2 gamma to 2, 70, 100, that's the 0.7. 2 gamma to 4 ground over 2 gamma to 2 ground is 0.05, 105. Okay? So if you are looking at the decay of a gamma band, then you take your measured gamma intensities, you divide by E gamma to the 5th to convert them into relative BE2 values. You might have to worry about conversion electrons as well, but okay, you get relative BE2 values. And you see, they look like 70, 105. And if they do, then this is probably a gamma band. We'll see what it looks like for a beta band in a minute. Okay? Here's a table, in fact, in a second. Here's a table, a lot of numbers. This gives initial angular momentum, final angular momentum, and different K possibilities. So this is a gamma band to a ground band, this is a beta band to a ground band, and these are other cases. Okay, so let's look at what we get. Here, for 2 to 0, 2 to 2, and 2 to 4, we have 0.2, 0.286, and 0.014. It may not have occurred to you, but those numbers are exactly 70, 105. That's where I got the 70, 105. Right? Clear? Those are in the ratio of 70, 105. Is that clear to everybody? Can you do that in your head? Okay. Sure? I'm not cheating. Okay? All right. What about for, so that would be for transitions from this 2 plus state to 0, 2, and 4. What about from transitions from this 2 plus state here to 0, 2, and 4? That's beta to ground. 0.2, same as that, 0.286. 0.515. That ratio is 70, 100, same, 180. So now, if we go back, to, let's say here, well, we can do it over here. So suppose we have a 2 plus state, and we don't know if it's the first state of the gamma band or the second state of the beta band. You look at the transitions to the 0, 2, and 4 of the ground band. You remove the E gamma to the 5th factor, and if they look like 70, 105, it's a gamma band. If they look like 70, 100, 180, it's a beta band. Clear? And this comes from being able to separate the rotational motion and the oscillation. To real data. So this is exactly the situation here. For 3 nuclei, gadolinium 154, rhenium 168, hafnium 178. Can you read this at the back? Okay, I can't make it any bigger because, well, technological reasons. Okay, I will read it to you. This is the initial state, 2, 3, 4, 5, 6. That's the 2, the 3, the 4, the 5, 6. For each one, the various final states, so the 2, 0, 2, 4. These are the oligorals. I didn't tell you those were the oligorals. Those squares of Lepsch-Gordon coefficients are oligorals. So 70, 105. Can you read the 70, 105? Okay. 70, 105. What's the data look like? 43, 114. 54, 107. 88, 106. Okay? So now, what do you say when you see that? You say, why doesn't the model work? Or, wow, look how amazingly well it works. Which do you think? You're supposed to have 70, 105, and you have, let's take this one, 43, 107, 14. Is that good or bad? Bad. Who thinks it's bad? Well, you got to raise your hand. You just told me it was bad. Who thinks it's bad agreement? Who thinks it's bad agreement? Come on, have some confidence. Who thinks it's good agreement? Who doesn't think? The sum has to equal the number of people in the room. All right, some of you are just afraid to express an opinion. All right. Okay, you want to know what I think? I think it's amazingly good agreement. Why do I think that? I think that because we're taking a nucleus with 154 protons and neutrons. We're saying it has a deformed shape. And we're calculating 3 relative PE2 values, transition rates, by doing nothing other than a Lepsch-Gordon coefficient. I mean, come on. That's an even greater approximation than replacing zirconium-91 by 1 particle in a box. I mean, it's astonishing that it works at all. Okay? You always have to be astonished if an absolutely simple model works at all. And then you can worry about making it better. Making it better always involves adding parameters. And one of the great philosophical questions facing physicists in any field is how many parameters is it worth having to improve the agreement? And not everyone will agree. Some people will say they'd rather have few parameters and very good agreement, or many parameters and much, much better agreement. And I'm not going to tell you which one is correct. There is no correct answer. It's how you feel about it. I have my own opinion, other people have their opinions. But regardless of that, here we have no parameters. And we got pretty reasonable agreement. This transition is substantially weaker than this, and this one is much weaker. Okay. Well, we can take another example. Let's take the 6 plus. 6 plus can go to the 4, 6, and 8. The oligorals are 27, 111. Here you have 12, 137. Now you notice a couple of things here. One is the agreement is worse here than here. And that in fact is a general rule. As the spin increases, the agreement gets worse. There's something else you notice. Take a look at these numbers and think about the spins involved. Here's a transition that goes from 2 plus to 0 plus. The spin decreases. The number experimentally is less than the oligorals. Here's a transition where the spin increases, 2 to 4. The number experimentally is more than the oligorals. Let's look down here. 6 to 4 decreases, it's less than the oligorals. 12 compared to 27. 6 to 8, it's more than the oligorals. 37 compared to 11. For almost all cases, you see that result. If the spin decreases, the transition is weaker than predicted by the Lepsch-Gordons. If the spin increases, it's stronger than predicted by the Lepsch-Gordons. Okay? So let me summarize this agreement. Okay, the agreement is remarkably good. indicating that these simple expressions are a reasonable first-order approximation. The deviations increase substantially as you increase the spin. Transitions in which the spin increases are nearly always larger the oligos, while spin decreasing transitions are nearly always smaller. And the deviations can become quite large, leading to factors of 3 or 4 discrepancies. These results are not just for this nucleus or this nucleus. They're universal over the entire chart of deformed nuclei. Always the deviations of the oligos get worse as the spin goes up. Always the spin decreasing transitions are weaker than the predictions. Spin increasing transitions are stronger. Now here's another philosophical one. Anytime you see something so regular, there has to be a simple explanation. Okay, so what's the simple explanation in this case? Well, the next 43 slides will show you what that is, but I'm going to skip them. They're also not here. The explanation has to do with this statement I made that the rotational frequency is very, very different than the vibrational frequency. And you asked me a question, and you said completely different. And I said they're not completely different. They differ by 3 to 4 orders of magnitude. But they're not totally different. And so there is some interaction or mixing between these states and these. Maybe that's an example of your beat phenomenon. Okay? And so if you introduce a mixing matrix element between these states, gamma band and a ground band stay in the same spin. That's a one parameter, you're introducing one parameter. You can correct all of these numbers very well and essentially get perfect agreement for all of them. Perfect agreement for all of these. By just introducing one mixing parameter. And the reason for this dependence on whether the spin goes up or down and the dependence on spin is that for a given strength of an interaction, it turns out, that's a property of raising and lowering operators, that the matrix elements become bigger as the angular momentum increases. And this business about the sign has to do with the sign of that interaction. It just means that the sign of that interaction is the same for all nuclei. Okay? Okay, that's the end of that topic. Everybody okay? Talk about spherical vibrators and ellipsoidal rotors. The question is, what happens between those extremes? Those are very simple extreme limits. How does deformation develop? One of the most intriguing and challenging, I think there's a word missing here, is the rapid onsets of deformation that occur in certain regions. For example, 150 samarium is a good spherical nucleus. 152 samarium is a good deformed nucleus. How can that be? Remember what we said about collector states? You add 2 protons. You don't expect a change? Well, this is an example where you do get a change. And that topic has been discussed in terms of something called quantum phase transitions, and one of you asked me about that. You asked about E5 and X5, so I added these slides in. So we'll talk about that, but let me just continue the introduction for a minute. You remember this slide from the beginning? I showed these. I used it to show that 2+ energies are high at magic numbers, and they fall off rapidly. And someone noticed that gadolinium, this green triangle, had a different behavior than, say, barium or cerium. Who was the one who asked that? Ah, good. Okay, so what I'm going to do now is discuss half of that issue, namely quantum phase transitions. And in the next lecture, I'm going to show you why. Okay? So first we're going to see what, and then we'll see why. Okay? Okay. So, you see this isn't all one smooth line. Okay? The different elements behave a little differently. Okay. I showed you a plot of R42 on the entire nuclear chart before. Here's another version of it, just a slightly older version. Color-coded, the red ones are near closed shells, less than 2. Blue ones are larger than 3.1. Here's the shell for the rare earth nuclei, which we usually talk about. By the way, why do we usually talk about that shell so much? It's because where the valley of stability goes, it goes right through the middle of the shell, and so you have all different kinds of nuclei. In many other shells, you only get, like for example, in this shell, you only have 3 of these rotational nuclei. Okay? There's another fact also. The shells down here are smaller, 8 to 20, 20 to 28, 10 particles or so. Up here you have 50 to 82, 82 to 126. The bigger the shell is, the more opportunity there is for structure to evolve. Okay, so here's R42. I'm going to look at this region. And you'll notice a fairly rapid change within 6 neutron numbers or so, from values near just above 2 to values near 3.33. It's a very rapid change in structure. How can that happen? What I want to do is, instead of looking at R42, look at differences in R42 for adjacent nuclei. And thanks to Berger for this plot. So red values are where R42 changes by just a little, blue ones where it changes big. And what you see is just after closed shells, or just before, you sometimes have a region where R42, in other words, the structure changes rapidly. Point. Okay. This is charge radii, and you see the same thing. This is in a different mass region, molybdenum strontium, but here you see charge radii or differences in them, and all of a sudden you get jumps at certain neutron numbers. That's again deformation setting. Ignore that. I had something over here which I deleted. I forgot to delete that. Okay. These sudden changes in structure are an example of a phase transition. Now, who studied phase transitions in solid state or condensed matter? Okay, so you all know that they only apply to infinite systems, right? Okay, nuclei are not infinite. So everything I'm going to say about phase transitions in nuclei is some kind of approximation. But it works remarkably well. So the way you study a phase transition, I think this will be the last slide before the break. Yes. Okay. You have something called an order parameter. That's something that describes what the structure of the system is. In our case, it's going to be the deformation. And then you have something here called a control parameter. In condensed matter systems, that's often the temperature. This could be the specific heat. In our case, it's going to be nucleon number, or neutron number. Now, the way you define phase transitions is in terms of whether derivatives of these quantities with respect to the control parameter are continuous or discontinuous. In nuclei, we have a big problem, because neutron number is discontinuous and you can't take a derivative. So again, we're going to approximate. Okay, so a classic phase transition for an infinite system, the order parameter, say it's specific heat or whatever it is 0, and then suddenly jumps up at some critical point. In a finite system, it'll look more like this. Here's an example of a first order phase transition. Some ice, some water. First order phase transitions always involve phase coexistence both at the same time. Yeah. Okay, so I think I will do this one. So there are 2 kinds of phase transitions in nuclei, second order and first order. I will not talk about this. Okay? This is much more interesting and important. So the idea of a first order phase transition is that the system has one structure as a function of the control parameter, in our case, number of neutrons. And then at some point, you can have 2 structures in the same nucleus. So what that means is the ground state will have one structure, one shape, excited state will have some other, and that lasts for a while, and then at some subsequent value of the control parameter, the ground state shape can't exist anymore, and you only have an excited one. So you have phase coexistence, they're both there, and a sudden change. Okay? And, okay. So let's take a break. I think this was a good compromise between your 2 wishes. You can discuss this if you want. Let's meet back here at no later than 10 after 3. Okie dokie. So, I just showed this slide a couple of minutes ago. And this is a slide of 2 plus states. I'm going to switch mostly to 4:2 ratios, R4:2, because as we pointed out, the absolute value of R42 tells us something immediately. So, okay. So I now want to look in some detail at the idea of quantum phase transitions in nuclei. This is R42 for those same nuclei that I put a circle around for the 2+ states a few minutes ago. And you notice something that happens here. First of all, you notice that they go from values around 2 or even a little less, which is a vibrator, up to values asymptotically at 3.33, which is a rotor. And this rotor, by the way, is really remarkably good. These nuclei, their R42 value is saturated at 3.33, not 3.34. It's really amazing. Anyway, there's a sudden rise here, and value around 3 is kind of a transitional value from this regime to this regime, and it occurs at neutron number 90. And remarkably, it occurs at 90 for all of these elements. So something interesting is going on at 90, and in the next lecture, we'll actually find out what that is. That's going to be the answer to why, to your question, to why this behavior is the same for all isotopes. So right now we're going to describe what the behavior is, but then in the last lecture we'll see why. Okay, so these are transitional. Now what's happening here? And one model of what's happening is the following. So this shows a potential, think of it as a potential well. It's not like the independent particle model, which is a box in which the nucleons move. This is a potential for the nucleus as a whole. If you remember when I talked about these two perspectives in like the second slide in the first lecture, these two perspectives are looking at nuclei from the standpoint of nucleons, or taking a couple steps back and looking at the properties of the nucleus as a whole. This is a potential relating to the nucleus as a whole. And so this is the energy of the nucleus as a function of beta, the quadrupole deformation, the amount of elongation. And 1, 2, 3, 4 refer to nuclei with different neutron numbers or nucleon numbers. So 1 would be the shape of the potential for a nucleus around here. This is 86 neutrons. Remember, 82 is magic. And so it'll be a spherical vibrator. This is a potential with a minimum at beta equals 0. And it's pretty steep, and so the nucleus will vibrate back and forth like that. As I add valence nucleons, I get to 2 here. 2 would be somewhere, I don't know, around here. And it has a different property. Excuse me. As a minimum 0, it's still spherical. But if you go to an excited state, there's another minimum corresponding to a non-spherical shape. And now if I go back a couple of clicks, that's the beginning of this phase coexistence, where you can have both a spherical and a deformed state coexisting, okay, for the same neutron number. Okay. If I go to 3, this would be correspond to the shape at 90 neutrons. The 2 minimum are degenerate. That's the critical point. Up until this point, the spherical minimum is always 1. The nuclei are spherical in their ground states and deformed in their excited states. After this point, point 4 would be up here, the nuclei are deformed in their ground states and they have an excited minimum for a spherical state. And so that corresponds to going along here, having phase coexistence, and then at some point, after n equals 90, only the deformed situation. Okay? Alright, so you get shape coexistence and you get a discontinuous change in equilibrium deformation. What happened? I clicked something. Okay. Here's another way of looking at the same thing. This is absolutely the same. R42 for samarium. This would be valence neutron numbers, so that's 84, 86. Potential with a minimum of spherical, 2 degenerate minima, and a deformed minima. Okay, another way of looking at the same thing. So here we're going to go from few valence nucleons to many. For few valence nucleons, we have a spherical potential with a minimum for a spherical shape. Nucleus can oscillate back and forth, so if you have momentary deviations from spherical, and you get a vibrational spectrum. R42 is about 2. The other extreme, you have a potential with a minimum for a non-spherical shape. You have an equilibrium beta, which is non-zero. The energies are rotational. R42 is 3.33. You have a deformed nucleus which can rotate. Okay? Yes?
Again, it's not clear why, because you have a certain number of neutrons and protons, it has to be deformed. I mean, you can have collective systems, not
You
deformed.
could have what systems?
Collective, I mean, many nucleons, and not deformed. Why they are most of the cases deformed?
Can I postpone that till the third lecture, where we talk about the proton-neutron interaction and how that leads to deformation? Okay, and now I'm going to say something which one person in the audience will be angry at me for saying. Sorry. In the fourth lecture, I'm going to talk about the proton-neutron interaction and how that's related to deformation, collectivity, how you can use that to predict the properties of almost any nucleus very simply. And a lot of that work is work done by Virgin. Sorry, I don't like to be pointed out, but I have to. And should I say the next thing about Florence? And in Florence, she also won the IUPAC Young Scientist Award in June, basically for that work. So she's going to miss that lecture because she's flying out today. She's going back to Istanbul, but since you're not going to be here, I have to say it. Don't be too late. Okay. So Maria, I'll postpone that and talk about it tomorrow. You had a question back there?
Yes, I wanted to make sure that this potential that you're talking about is the potential made up of the whole interaction, like the bulk potential.
Yes.
Right? That would be the main term in the shell model.
No. The shell model potential refers to a box, a potential in which each nucleon orbits. And so the distance coordinate would be the radius from the center of the nucleus. This is a potential describing the motion of the nucleus itself, okay, and its deformation. So this axis here, beta, is the amount of ellipsoidal deformation. So this is a potential for the many-body system as a whole, and the one you were mentioning is that for the individual nucleons. And that's why I wanted to make, I hope that distinction is clear to everybody.
So this potential reflects the difference, the variations in energy of the nuclei, but then nucleus in this case, with the variation of the deformation.
Exactly. Okay? Very important distinction. Now, some of you may have noticed there's a gap in the middle of the slide. This gap is going to show you what happens in the transitional region, and you've already seen it. So why am I showing it? I'm showing it because when these data were discovered, basically around 2000 and 2001, Franco Iachello, who was also the inventor of the IBA, came up with a model for these quantum phase transitions, which is so stupidly simple that it can't possibly work, but it's another example of a stupidly simple model that works extremely well. And he said, well, how can we deal with such a complicated expression, a complicated potential? And he said, the essence of these things is to simplify it down to its essential points and not get hung up on the details. So he said, look at that little bump, let's ignore it. Look at this sharp rise, let's approximate the whole thing by a square well. Okay? So he said, let's do a square well. Now it's a square well in 5 dimensions, and that introduces some little strange things. But if you solve a square well in 3 dimensions, you know the solutions are Bessel functions of integer or half-integer order. The only difference here is the solutions are Bessel functions of orders which are irrational numbers, but that's a detail. Okay, so this situation is called X5 for reasons that are not important. And I'm going to show you what the predictions are. So, well, okay, I forgot that I had this. So this is the situation we're dealing with. This is the critical point, square well, Bessel equation, the solutions have irrational order. Big deal. Okay. Here are the predictions. Now, the most amazing thing about these predictions is they are parameter free. They do not depend on any parameters. They only apply to nuclei that look like this, so you can't apply it to linoleum-275. But they apply to nuclei at the critical point, and it's an infinite square well, so there are no parameters. All these predictions are just what they are. They either agree with the data or they don't. And there are a number of predictions here. You can see transition rates, energy levels, blah, blah, blah. I'm going to simplify this and just look at the lowest few levels, because this is too complicated. So here's another way of looking at it. So the energies go as 100, 291, 545. Look at that, 291, 100. That's an R42 of 2.91. So it's right in between the vibrator and the rotor. You have an excited state. Now this is a very interesting fact. In most collective models, the energy of this excited state is a free parameter. Here, since the square well is a square well in the laboratory system, it includes all the angular momentum and everything, this is a prediction. This energy is at 5.67 times this energy. So the model predicts there should be a 0 plus at 5.67 times the 2 plus energy. That's there. It also predicts that the 6 plus of the ground state band should be about the same energy as the 0 plus, first excited 0 plus state. Weird predictions. Okay, and then all these BE2 values are also defined. It says that the BE2 values in the ground band should go as 100, 158, and 198. I didn't tell you this, but in a pure rotor, they go as 100, 143, and some more I've forgotten. In the vibrator, they go as 100 and 200. So this transition in the vibrator is 200, in the rotor it's 143, and here it's intermediate. These BE2s are larger than these. It's a whole bunch of predictions. Here's the comparison with the data. X5 is Marion 152. So first of all, R42. In X5 it's 2.91, in the data it's 3.01. X5 predicts that the excited state, R42, this ratio should be less, and it's less. Here you have BE2s, 144, 228, 285, 144, 209, 245. Here you have BE2s which are smaller than these. Here you have BE2s which are smaller. Here you have all sorts of transitions between these two bands. Here you have all sorts of transitions. The 0 plus state is predicted to be at 5.67 times the 2 plus. It's experimentally at 5.62. This is all parameter free. All he did was take a square well. For example, these spacings here are a lot smaller than these, and these transitions are a lot stronger than these. And there are very simple explanations of those, which I am not going to tell you, and the reason is just time. They have to do with the fact that the well is infinite, the middle wells are finite, and so on, and the fact that a rigorous square well is too much of an approximation. If you slope the outer wall, you get better agreement. And if you want to ask questions, I have the slides at the end, but I skipped over them to continue. Okay? Just another way of showing the energies. These are the energies in the ground band. The vibrator energies as a function of angular momentum, you remember, are uniform. 0, 2, 4, 6, 0 phonon, 1 phonon, 2 phonon, 3 phonon. In the rotor, they go as the square of the angular momentum, J times J plus 1. In X5, they're intermediate, and those are the data. In the excited 0 plus band, this is an interesting point, and it also gives you another idea about how to look at nuclei. Here we saw this apparently big disagreement in energies, right? Is this just energies that are wrong, or can we somehow isolate the key point? What this slide shows is that if you take ratios of energies within that band, they agree exactly with X5. So what that tells you, oops, wrong way. What that tells you is this enhanced set of spacings compared to this is not just wrong images. It's solely an issue of scale. The scale here is too big. It's not just the individual numbers that are wrong, because if I normalize them to this spacing, I get perfect agreement. So, learning that it's scale allows you to focus on what could possibly be the explanation. And I have slides to show you the explanation if you want. Okay, so the collective models we've talked about have all been introduced ad hoc. Okay, I just said, let there be a collective model. Let there be a vibrator, let there be a rotor, let there be a quantum phase transition. And there was. Okay. It would be nice if we had a single model that had all of these things in it. And so the question is, is there? Well, there are two. One is called the geometric collective model, GCM. Are any of you theorists, or expecting to be theorists? Okay, if you're going to be a theorist, you will think of GCM eventually as generator coordinate method, so don't be confused. Okay, geometric collective model and the IBA. The IBA is much simpler than the geometric collective model. It has fewer parameters and works better. So I'm going to very briefly summarize the GCM in about 2 slides, and then focus on the IBA. Let's remember our problem. The problem is that when we talk about heavy nuclei, like samarium or gadolinium or whatever, or uranium or thorium, the size of the bases, the number of states, is simply so huge we have to make some approximations. And so, what we do is, we do what your question at the back was all about. We consider the nucleus as a whole, we look at our potential, or some other model describing the nucleus as a whole. The geometric collective model says, let's write a potential in terms of these beta and gamma parameters. Beta is the ellipsoidal deformation, gamma is the amount of axial asymmetry. And so you write Hamiltonian, which is kinetic energy plus some shape like that, some potential like that. And so here's the geometric collective model. And the easiest way to write it is a power series in beta, beta cubed, beta to the fourth, and some function of gamma. There are altogether 6 terms in the model. Nobody ever uses more than these 3. Very clear in the model how to extract the parameters. But I'll just give you an example of how you can use it. Suppose I have a potential that looks like that, and it's flat in gamma. I can approximate that by V equals C times beta squared. So if I have a good spherical vibrator, that's the Hamiltonian potential. Suppose I have a nucleus with no dependence on gamma, in other words, the axial asymmetry can vary, and a deformed minimum. Then I have a term in beta squared and a term in beta fourth with opposite signs. This sign will be negative. That means the potential will start off small. Eventually, beta to the fourth will get bigger than beta squared by any arbitrary amount. And so if C4 is positive, the potential will turn around. So I've made a minimum. If I have a shape in gamma that looks like this, I can have this, and then I can have a cosine phi gamma. So with these 3 terms, I can produce all these shapes, and I can fit any nucleus. That's all I'm going to talk about that. Okay. Now, can you guess what topic is coming next? Okay, the idea. Okay, these are big letters because I think this is by far the most successful general collective model. Okay, now, the IBA is sometimes thought as a group theoretical model, sometimes thought of as a collective model, and sometimes thought as a shell model. And the reason for that is because it's really all 3. It's a huge truncation of the shell model, and I'm going to talk about that aspect of it first. First of all, as with many models, it only looks at the valence nucleons. It says we just completely ignore all the others. Then it says we will only allow certain configurations of all these valence nucleons. will only allow pairs of valence nucleons coupled to angular momentum 0, which we will call, all pairs are going to be bosons, which we will call S bosons, and coupled to angular momentum 2, which we will call D bosons. Now, why would you make that approximation? Does anybody know? When I click this, the answer is going to show up over here. Why would I assume that the low-lying collective states are made up of only angular momentum 0 and 2 pairs of fermions? Pairs of fermions, 2 fermions. 2 fermions. These are hints. Yes?
So the reason we want the speed to be a unit or a zero?
I'm sorry?
For the speed?
Say there's a sentence.
Is there
Turn on your microphone.
Sorry.
Is there a reason you want the spin to have a specific value?
I can couple pairs of particles to many different angular momentum. All right? I can couple 17 or 18 protons and neutrons to some angular momentum 32, or whatever. I can couple 2 protons to spin 4 or 6. The model assumes only 0 and 2. Why did Iackello make this approximation? What could have motivated them to think that these would be important? What motivated them to think that 2 nucleons might prefer to be in 0 or 2 states? Yes?
They're just copying the electrons?
No? You're really hung up on electrons, aren't you?
Yeah.
We view them as something that gets in the way. Anybody have an idea? Anybody want to think about what the spectrum of a nucleus looks like with 2 particles outside the closed shell? What's the lowest spin state? Did you get that? What's the, you should be answering. What's the next state? What's the next state? 0 and 2. If you have 2 particles, 2 identical nucleons, they prefer to couple to 0 and 2. The rest are higher. Now, they're not so high, but Iackello and Reed, who invented this model, said, let's assume that that's the only thing that matters. Again, there's no way that that should work. Okay, then they defined a simple Hamiltonian in terms of S and D bosons and simple interactions. It has a group theoretical underpinning. And why would we pay attention to any model that is so extreme? And the answer is because it works and it's very parameter efficient. Now, if you remember in Samaritan 154, you can make 3 times 10 to the 14th 2 plus states. Are you leaving because I don't like electrons?
I'm sorry, I'm not smart.
Okay. Go work with your electrons. Samaritan 154 has 3 times 10 to the 14th 2 plus states. In the IBA, the IBA for that nucleus has 26 2 plus states. So now think, here's Frankos and Iackello sitting at the desk saying, oh, how are we going to treat Samaritan 154? It's got 10 to the 14th 2 plus states. And one of them says, oh, let's make a model where we pick out 26 of them and assume that that takes care of 99% of the physics. Now, anyone walking by the office at that time would have said you were crazy. Okay, now maybe they are crazy, but it works. I'll show you that. Here's a cartoon of the space of all the shell model configurations. And here's what the IBA is equivalent of. So they're about gazillions. Now, if I showed this to scale, you wouldn't see that. Right? It's 10 to the 14th time, 10 to the 13th times smaller. But I blow it up so you can see it. And the IBA is equivalent to considering only these special configurations. Okay, let me say it in a different way. This is kind of an animated way. Let's look at Samaritan 154. In the shell model, it has 3 times 10 to the 14th 2 plus states. We need to truncate this because we can't solve it. The IBA assumes that only valence nucleons, fermions go as pairs of bosons, only angular momentum 0 and 2. And if you truncate the shell model by doing this, then wind up with 26 duplex states. And the question is it conceivable that these 26 basis states are chosen correctly to account for the low-line collective states? And the absolutely remarkable thing is yes. Okay. Now, I think I'm going to skip the group theory, generating algebras, and I'll just give you one little taste of it. The Hamiltonian is written in terms of creation and destruction operators. You all know about creation and destruction operators? Yes?
Yes.
Okay. Okay. We're going to create an S boson or destroy it, create a D boson or destroy it. And so these are the operators. Now, the operators have to occur in the Hamiltonian in pairs like this with equal numbers of creation and destruction operators. Otherwise, that term in the Hamiltonian would change the number of valence nucleons. So to stay in the same nucleus, you have to have combinations like this. So these are the basic ingredients of the model. How many of these terms are there? Well, S dagger S is one of those. S is angular momentum 0. S dagger D, there are 5 of these terms because D has angular momentum 2 and it has 5 magnetic substates. D dagger S has 5. D dagger D has 25, 5 plus 5. And if you add that up, you get 1 plus 5 plus 5 plus 25. That's 36. Whenever you have a system of operators that comprises a certain number like 36, take the square root of it, and that's a good guess as to what the group structure will be. And it can be shown that this corresponds to a group called O6. Now, U6, sorry. I'm not going to go through the rest, okay? I can do it next time if you want. You can see why I want to skip it, because it's clicky. I talked about generators and Casimir operators, and it's down representations and so on. And it takes a while to go through all that. And I illustrated the idea of group degeneracies and so on. Okay. Now, there are 3 subgroups of U6 that describe different physical structures. They're called O6, U5, and SU3. And I just want to give you an example of what it means to have a group structure. If I have a group called O6, what it means is this. U6 is the most general group in the IBA, and that just is a group where all the levels of the nucleus with N bosons are degenerate. Now, a model where all the excited states of the nucleus are degenerate with a ground state is actually not as bad a model as you might think, because the next nucleus has 2 GeV higher energies, it's got 2 more neutrons or protons. But in terms of discussing the excited states, it's not a very good model. Okay, so that's not going to be sufficient. You then introduce another term in the Hamiltonian, which is described by a subgroup, and these levels split. Okay, now here you would have a nucleus with 3 excited levels, with 2 ground state 2. That's not very reasonable. You add another term in the Hamiltonian, and these levels split. So do these, I just didn't draw them. And you add another term, and they split. And so you wind up getting different families of levels. Each step, each term in the Hamiltonian breaks the degeneracy and adds a new quantum number. Here you have a quantum number sigma, a quantum number tau, a quantum number angular momentum. So that's the concept of one of these groups. I haven't gone through the details. I can do it at the end tomorrow if you want it. The idea is that each term in the Hamiltonian introduces a subgroup, introduces a quantum number to label the states, adds an eigenvalue term in the Hamiltonian thing, and breaks the previous degeneracy. Okay, but now another cartoon. I like these. So here's the group structure. You have U6. This is the formal definition of what goes on here. Magical group theory stuff. You get these 3 different groups. U5 corresponds to a vibrator, which we've seen. SU3 to a rotor. O6 to a gamma soft nucleus. If you have 3 things, you think of a triangle. And so this is normally depicted in this way. You have a triangle describing all the possible solutions to the IBA Hamiltonian. Each one of the corners corresponds to one of these limiting cases. A vibrator is a spherical nucleus, right, which can vibrate. A rotor is a non-spherical nucleus. This is non-spherical. And so This region of the triangle is spherical, this is deformed, this is called the symmetry triangle, the IBA. And the idea is if you are dealing with a nucleus and you want to try to describe it with the IBA, you use the Hamiltonian to position the nucleus somewhere in the triangle. And we'll see how to do that. This just shows it again, and just shows little level schemes of the lowest levels in each case. In the vibrator, you have the ground state, the 1 phonon, the 2 phonon triplet, 420. In SU3, you have the ground band, the gamma band, the beta band, 06, you have some other levels. Here you have R4 202, 2.3.33, 2.5. You have a question? Okay, now, very few nuclei actually look like these idealized symmetries. If I named all the ones that look like these, it would be less than 5 or 6 or 7. So most nuclei are not at these corners. And so if that's all the model did, it wouldn't be very useful. But we want to figure out how to use the model in a much more general way. Okay, so I'm going to use, if I have my hand down here, it's somewhere wrong. I'm going to use this idea Hamiltonian. Now let me try to explain this a little. This Hamiltonian has 2 terms. The first term has only the number of d bosons. Now remember, the nucleus has, let's say, 20 valence nucleons. That's 10 bosons. These bosons can be s bosons or d bosons. A given state, let's say the ground state, can have 6 s bosons and 4 d bosons, or 5 and 5, or whatever. Or if I introduce interactions, it can have mixtures of terms. Okay? Okay. First term in the Hamiltonian just asks, how many d bosons are there? And epsilon is the energy of a d boson. We set the energy of an s boson equal to 0. This term, kappa QQ, is a term where the Q operator is this. This changes the number of s and d bosons. D dagger s, s dagger d, destroys the d boson, creates an s boson, and so on and so forth. Okay? This term, or this term, will mix wave functions that have good d boson number. So this is introducing collectivity. Is that clear without my having really gone into detail? You have a set of basis states. Each basis state is defined a certain number of s bosons, a certain number of d bosons. If you only have the first term in the Hamiltonian, this is 0, you would have a perfect next set of states, 2, 3, and so on. If I make kappa non-zero, this term changes, mixes those basis states. Okay? And we begin to get collectivity. Okay, so you can think of this Hamiltonian in terms of the triangle. There are only 2 parameters. There's kappa over epsilon, the relative size of these 2 terms, and there's a parameter chi inside the Q operator. Kappa over epsilon basically tells you how far you are from the vibrator toward the deformed side. The bigger kappa is, the more this term dominates, the weaker this one is. This gives you a spherical vibrator, this gives you deformed nuclei. Chi has to do with the axial asymmetry, that is the squishiness. Okay? And I think I said that epsilon and d counts the number of bosons, corresponds to a vibrator. This gives deformed nuclei, and chi determines the axial asymmetry. Structure is given by 2 parameters, epsilon and kappa, and chi only. 2 parameters. Okay, there are more complicated forms of this Hamiltonian with up to 6 terms, and some people like them, so I can't tell you this is the only way to do it. I would say if you made a pie chart of how many IBA calculations are done with this versus the one with 6 terms, it's about 98% to 2%. But there's some very well-known and famous theorists spread over different continents who think that you should use the 6 parameter form. That's fine. Okay. This form works pretty well in most cases. I want to just relate that Hamiltonian to the symmetry triangle more explicitly. This term alone gives you U5. This term gives you either SU3 for a specific value of chi or O6 for a different value of chi. Okay, so this, I say later, but it's actually now. This allows us to calculate a nucleus anywhere in the triangle just by choosing the parameters. Okay, so what's the simplest possible solution? The simplest possible solution is this Hamiltonian, and as I've already said, that corresponds to U5, and it just gives this vibrator spectrum. I'm going to skip that. And here's an example we've seen several times. SU3 looks like this. It has a ground band, it has a beta band, it has a gamma band, it has some higher bands. Notice that the beta and gamma bands here are degenerate. So if you really had an SU3 nucleus, you'd have to use things like the Oliger rules and other techniques to determine which orbital state goes with which band. Okay. Characteristics of SU3 are degenerate bands within a group. Zero BE2 values between groups. The selection rule is you can only have transitions within a group. So the IBA and the SU3 limit predict there are no transitions from year to year. Now that's not quite as stupid as it sounds. If you remember when I summarized the data, the transitions within a band are like 200 Weisskopf units. The ones between are like 5 to 15. So in first order, these are small. In second order, they're not zero. And so that tells you that real deformed nuclei are not going to be SU3. You're going to have to break SU3 and go into the triangle. Okay. I think I already covered this. Okay. So this has two parameters, epsilon over kappa over epsilon and chi. I want to talk about parameters. I said a little while ago that different people have different views about number of parameters, whether you want to use fewer parameters and get good agreement or more parameters and get great agreement. My preference is always the first. And who's heard of Egal Townley? Who knows of the Shellmo textbook, Townley and Dushali Townley? Oh God, sick transit over here. Oh, very good. Okay. So Townley's a very wise guy. And he said once, and I think he was quoting somebody else like Dirac, he said, give me two parameters and I can make an elephant. No. He said, give me three parameters, I can make him fly. I say, give me 5 parameters, and I can do all sorts of amazing things. So it depends what your philosophy is. My philosophy is always over here, Pete Bentley Sackers is over here, for example. Who's heard of Pete Bentley Sackers? I thought you were very Pete. He's a wonderful guy. He and I disagree.
It's true that there are only 2 parameters, but
Yeah.
I think them for every other weakness.
Yes.
So in a sense, looking at it differently, it's 2 times the number of parameters.
Okay, so that's a very important point. If you have a shell model Hamiltonian, Coulomb terms and other terms and so on, you can calculate one nucleus with the same Hamiltonian, you can calculate the next. And this is a model with predictive power. It can predict what a nucleus will look like. When you talk about collective models, you have to feed them. They can tell you what the nucleus is doing, they can't tell you why. So with a model like the GCM or the IBA, it cannot predict the properties of any nucleus ever. But if you feed it 1 or 2 observable quantities, it can predict a tremendous amount of other things. So you're absolutely right. It's not a predictive model in the sense of ab initio. You have to feed it a couple of observables, and we'll see how to do that in a minute. Okay, in fact, we're going to see now. H has 2 parameters. Now, a given observable, all right, can only specify one of them, right? But the triangle is 2-dimensional. If we want to identify where a nucleus is in the triangle, we need some help. Let me illustrate this. Suppose we have an R42 value of 2.9. Where is the nucleus in the triangle? Well, here R42 is 2, and here it's 3.33, so it's somewhere along here, right? Is that clear? Clear? 0.3. So somewhere along here, there's also 2.9, right? In here, here's R42 of 2. Here's a value which is between 2.9 and 3.33, say 3.1. So somewhere along here, R42 will be 2.9. So just specifying R42 just gives me a contour. And this set of structures here varies tremendously. These are nuclei which are gamma soft. These are nuclei which are transitional between a vibrator and a rotor. So I need another parameter. I need another observable to fix where we are. Okay? Okay, and so now I'm going to illustrate the idea of orthogonal crossing contours. These are contours of constant R42. If I go back here, here's one of them. Come on. That would be one of these. If I take other R42s, like 2.2, 3.3, they correspond to these contours. What I'd like to find is an observable whose contours run this way. Because then where they intersect, I can pinpoint the parameters. Well, it turns out there is one. It's the energy of the second 0 plus minus the energy of the second 2 plus over the energy of the first 2 plus. Why this? I'm not going to tell you. It just happens to work. These contours go this way. So suppose we now have a nucleus with that value of R42 and this value of this quantity. What do? I find out where they intersect. Orthogonal crossing contours. And distance this way in the triangle is kappa over epsilon. Distance this way is chi. So this point corresponds to some value of kappa over epsilon, and this angle corresponds to some chi. And so now I can make a prediction. Here is some data on platinum 194. What you see here is, I don't know, 10 or 12 excited energy levels, maybe 30 transitions. I use these two parameters to fix the properties. And over here is going to be an IBA calculation. And you can see that it works amazingly well. The thickness of the bars is proportional to BE2s. And it's just astonishing how well it works. And you can see we do this. Okay? Here is another calculation. Erbium 168. These are the data, ground band, gamma band, beta band, higher bands, and these are the IBA calculations. The agreement is pretty good. So the model works pretty well. It has the fewest parameters of any collective model and works the best. It doesn't predict the nucleus without knowing something. You can't go to osmium 242 and make a prediction. And this is just a summary, for example, the different trajectories. Each one of these trajectories is an element like a terbium, different isotopes, and forget this thing. And this just shows where they are in the triangle. So that's an illustration of a set of IBA calculations. And interesting question will be, two interesting questions. What happens far from stability? What happens if you have weak binding? And another thing is, it comes back to this issue of the complementarity of microscopic and macroscopic. What we've learned here is what nuclei do. We want to know why. Why do certain ones exhibit certain symmetries? And one of the keys to that is the proton-neutron interaction, which I will talk about next time. Okay? And we'll also learn a very, very simple way of predicting the property of any nucleus by simply multiplying two numbers together, each less than 22. And that will work out better than any supercomputer calculation with thousands of hours. Yes? So I'm done.
Okay, so this model you put into things, then you pinpoint where you are on this triangle, and then what happens, what do you learn when you see that you don't reproduce what you see?
Aha! So what do you learn when you take any model and don't reproduce something? Okay, it tells you any number of things. If the model is really, really good, it could tell you the data is wrong. Maybe you should go and remeasure. And I can't tell you how many times that's happened with the IBA. It's been an IBA prediction which worked very, very well except for one transition. People went back and measured it and found out it was wrong. Okay, but let's assume the data's right. It tells you there's something missing from the model. So what could be missing from the IBA? Many things. We didn't make any distinction between protons and neutrons. We simply took the total number of valence nucleons and assumed that the protons and neutrons are doing exactly the same thing. Maybe they're not. Who's heard of mixed symmetry states? Okay, mixed symmetry states are states where the protons and neutrons are wiggling like this. So if you want to describe those, you can't use this model. You have to introduce a new model, which exists and has a name called IBA2, which separately takes into account the proton bosons and the neutron bosons. Suppose you want to predict the properties of an octopole set of states, 1 minus 3 minus 5 minus. You can't possibly get it out of this model. The two bosons both have positive parity, right? So you have to introduce something else. There's a version of the IBA called IBA-SDPF. Has a P boson and an F boson, angular 1 and 3. Then you can try to predict octopole states. Okay? So there are all sorts of things you can do. You can introduce G bosons. Remember in that level scheme for 2 valence nucleons, you have 0, 2, 4, 6. The 4 isn't so much higher than the 2. So maybe you should have a G boson. Okay? All of these things introduce more parameters. Okay? And so it's a question of taste. Do you like to have good agreement with maybe a few problems with 2 parameters? Or do you want to have 12 parameters and perfect agreement? Essentially. So, and I can't tell you the answer to that. Everyone has their own opinion. But the first thing is you can ask, is the data right? Second thing is, what does the disagreement tell you? And it always tells you that there's something that you can improve in the model. And that's basically the history of any model. Someone invents a model, and the model is always simple. And they see that it works for something. And people go, oh, look, it works. And then somebody else who wants to get a visitor letter says, well, it doesn't work here. And they publish something that says, oh, there's a disagreement. And then somebody else says, wait a minute, we can fix that disagreement by changing the model. Remember I showed you that in the X5, that the BE2 values between those two sets of states were much bigger in X5 than experimentally, and the energy spacings were, so that's a perfect example of this kind of thing. That was noticed right from the beginning, and people tried to work out what could be the problem. And why don't you ask me at the end of tomorrow? I have 2 slides that I'll show you. But it led to realizing certain improvements in X5 at the cost of parameters, but that explain those problems. Okay, great question. It always comes up.
I have another question. Suppose I have a nucleus and I know...
So is what?
I have some nucleus and I know these input parameters. How long does it take an IBA calculation in time consuming?
Okay, so just, you have a nucleus and you have 2 parameters.
You have the things you need, so the R42 and then the other
thing,
the ratio.
we call it R02, yeah.
Okay.
How long does it take to do the calculation?
Is it hard? Does it take?
It takes, a millisecond,
Okay.
okay? In fact, there's a version of the program where you can vary the parameters with a little toggle online and it makes a movie of the level scheme.
Can you find it? Can you do it online, the IBA calculation?
I don't think I can do that one online because last time I tried it was broken, but I can do a calculation online. I can do that next time. At the cost of something else, but yeah. I can do that. You want me to do that?
It would be nice to see it.
Who would like to see that? Who doesn't want to see it? Who doesn't care? Who's asleep? Who wants to get out of here? Okay, so would you do me a favor? Would you email me tonight, richard.casten@yale.edu. Email me about 8 o'clock and remind me to do an online calculation tomorrow. Okay? And I'll set it up. I mean, in principle, I can do it in 3 minutes here, but if I try to do it, I'll screw it up. Other questions? All right.
Because of course you have different systematics. So when I see how you define the parameters, you need the 0, the 2, the 4, and you need the next one. You need the 2 plus for the next one. But one of them is collective, so I can take the parameters from the next nucleus or the previous one, because it's always closer to stability, more far away from stability. So my question comes when I induce the parameters like that, because my knowledge is reduced, how far I am from really a good representation of the nucleus.
Okay. So did you all understand the question? I said earlier that these collective states vary slowly with N and Z. And so maybe you don't know all these levels in the next nucleus. Suppose you assume they're the same as in the previous. Can you do the calculation? And the answer is yes, you can. You will get, in general, reasonable agreement. In cases where the structure is changing rapidly, of course you won't. But you can see here, for example, take a terbium. This is about 10 even isotopes. So the change from one to another is relatively small. By the way, notice one other thing. This will take me a while to get back to. Scales as the total number of bosons. This term scales as the square of the number of bosons. So imagine you had absolutely constant parameters and went from boson number 2 to 6 to 10 to 16. Without changing the parameters at all, the structure would change. So the model automatically includes an evolution from vibration to deformation. If I take constant parameters and have n equals 2, this term will be very, very small. If I have n equals 16, this term will dominate even if epsilon is big. So you get certain variation even for constant parameters. Okay? It just depends how much the nuclei change. One more question. We gotta go. One more question. You look like you have a question. No? You look like the question was bubbling up. No, okay, I don't want to embarrass you.
I guess the question is, because this is only valid for even nuclei,
Yes.
what do you do with the
Okay.
even? I guess that's the next question.
Okay. So for odd mass nuclei, there's a model called the IBFA, interacting boson fermion approximation. If the odd particle can only occupy a single orbit, like say I13 halves, that model is very simple and works very well. If that particle can occupy several orbits, like any of the orbits in a full shell, the number of parameters goes as the cube of the number of different orbits it can occupy. So if it can occupy one orbit, you get one more parameter. If it can occupy 5 orbits, you get 125 more parameters. Think what your elephant can do. Okay? So the IBFM is a very nice model. It's been used mostly for unique parity states. Going beyond that is very, very tough. There's also an IBFFA. If you take 2 particles and break a boson and couple them into a 2 quasi-particle state. There's also an IBA3, which takes isospin into account. And, okay, they're all different versions. Any last question? Oh, you do? Good. Turn on your microphone. I hope I didn't embarrass you, but it looked like you were.
What kind of prediction you can do with this model that you cannot do, for instance, with the model still like looking this shape resistance region? You can have also prediction of level scheme and transitional matrix element from the model where you start from the shape of the potential, surface potential energy, and then you build up to your...
Okay, so you mean what I call the geometric collective model? Or you talking about X5?
The one called beyond mean field model.
Okay, so
Yeah.
if you can have a potential This is what I call the geometric collective model, where you have a potential written in terms of beta and gamma. That model, I showed you a Hamiltonian where V of beta gamma had 3 terms. The full Hamiltonian has 6 terms, up to things like beta to the 6th power. Okay? And a kinetic energy term. And it always has at least one more parameter than the IBA. And very often 2 or 3 more parameters. And you run into the elephant problem. It's very hard to find a unique set of parameters. I can show you, I think I can find a